Hello, 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 hello. సాయికి మాత్రం వస్తుంది. ఎలా?
Yes. Yeah. Yeah. I don't know. Uh, like, is it okay? Yeah. I just the back. Okay. Testing. Testing. Okay.
A couple of minutes.
Okay. Okay. Sorry.
Welcome everyone. This session. We will have one talk. Unfortunately, the other authors couldn't make it. So we are happy to welcome Bernardo. He'll be talking about bandwidth of time.
Well, thank you very much. I'm very glad to be here. Is everyone hearing me all right? Okay. Yeah. Okay. So this talk is this paper I did with my supervisor and a fourth co-author. So it's called the Bandwidth of Timed Automata, 3 classes, and it talks about time languages. So what are time languages? So you may all know discrete languages. So a discrete language is a set of words, and yeah, there seems to. Oh, okay. Yeah. If you could put it in your book. Oh, yeah. Yeah. Okay.
It's right now.
Yeah.
Keep it in your pocket.
Okay. Is it all right like that? Okay. Okay, so I'll start over. So yeah, we're talking about time languages. So you may know discrete languages. So a discrete language is a set of words, and a word is a sequence of letters from a finite alphabet. Well, now a timed word is very similar. It's a sequence of letters from a language, except that for each letter we associate a timestamp. So we may see this as events occurring at different instants, and each event is a letter. So we can represent this as a set of words that fall on a timeline, and then a time language is just a set of timed words. Okay, so our goal in this talk is to, well, our general goal is to come up with a way of quantifying information for time languages and maybe to find some application for information theory, so theory of coding, transmitting information, etc. So in this talk, I will present the notion of bandwidth, which we introduced in a previous work, but which is very fundamental to what we're doing here. So which is a way of quantifying information per time unit in a sense. Then I'm going to present to you timed automata and some of the usual tools that are used to analyze these automata. Of course, timed automata give a regular class of time languages, and then I will classify automata. There's a typo there, sorry, according to their bandwidth. Okay, so how do we quantify information in time languages? So something we can do for discrete languages is that we take n-letter words and we count how many words are there of length n. So, I mean, we can start by doing that, and we want to do the same for time languages. So we want to take words of a certain duration, so every word of length at most t, and we want to count them. But of course, there's a problem because time being continuous, there can be very easily an infinite amount of words. I mean, we can take just words of duration 1 second. We can already have very simple languages that have an infinity of words. So we're not counting words, but we're counting words up to some precision. And for that, we're using a notion introduced by Kolmogorov and Tikhomyrov, which is epsilon entropy and epsilon capacity. So if we have a continuous set, like for instance, I mean, this is a representation of it. So we will look at a set of points inside of it, such that each point in the continuous set is epsilon close to one of these little dots. So that is an epsilon net. An epsilon net is in a way something a set of dots that covers up to some precision all of the continuous set. And respectively, we have also the notion of an epsilon separated set, which is a set of dots inside the continuous set, so that every 2 dots are epsilon far from each other. So ideally, what we want is when we have an epsilon net, we want to cover all of the continuous set. What we want to do is cover it with the minimal amount of dots possible. And when we have an epsilon separated set, what we want to do is to fit as many dots as we can. So we want the maximum number of dots we can possibly get into the continuous set. So these minimal and maximal values, if we take the logarithm, we get the notions of epsilon entropy and epsilon capacity, which were introduced by Kolmogorov and Tikhomyrov, and which give this idea of the information in a set up to some precision. So these two values are very similar to each other. And okay, so now that we have these notions, the question is, well, how does this look for time languages? And to do that, we need to define what do we mean when we say to be for 2 timed words to be epsilon close to each other. And so we have a definition so we need to come up with a definition of a distance. Well, this is not really a distance, it's a pseudo distance, but it works as well. And I'm not going to too much detail of the definition, but so if we have, I will explain quickly, if we have 2 words U and V, and we want to verify that they are close to each other, so we look at any of the 2 words, U or V, and we'll look at each of the letters in the word separately, independently. And we want every letter in U to be approached by an identical letter in V, which is in more or less the same timestamp. And more or less, I mean in the same timestamp or in a radius of epsilon, basically. So here these letters are approached by letters that are not very far from them. And so that's our main notion of epsilon closeness. So then what does an epsilon net look like? So I have a little example here. We have this language in which we have a letter between 2 and 3 and a letter between 4 and 5. We want to approach this with precision 1/4. So we have to approach the first the letter on the first segment and the letter on the second segment, and because we want to approach this with epsilon equal 1/4, we need 2 points on each segment to approach this. So this gives I mean, if we take all the possible combinations of this, we get for timed words. So we're approaching this language with 4 timed words, so that the epsilon net of this language is 4. So its epsilon entropy. So its epsilon entropy is the logarithm of 4. So we're taking logarithm base on base 2. So that's an epsilon entropy of 2. Okay, so now that we've defined this way, epsilon entropy, this way of quantifying information in time languages, we can get to our notion of bandwidth. And so the bandwidth, so we're trying to get information per time unit. So we said epsilon entropy is, in a way, the quantity of information in a language. So we're taking the language up to length t. We cannot take a language of unbounded duration, because then the epsilon entropy would be infinite. But we're taking up to t, and we're taking the rate over t. So that's, in a sense, the quantity of information per time unit. And we're taking the lim sup when t tends towards infinity to have a kind of a stable behavior of the language. So, well, this is similar to what we can do with discrete languages, in which we count the n-letter words. We take its cardinal, and we take the limit of the rate over n. Okay, so this notion was introduced in our previous work, and we basically, in which we basically introduced this notion, and we found that there was some relevance, even though there were some missing details, but there was some relevance for theory of coding. So we're confident that we have kind of I mean, we believe that we have a relevant notion here. Okay, so now what we want to do is we have this notion, but we want to be able to compute it, because, I mean, all this talk about epsilon nets and epsilon separated sets, it's not very clear how we can, well, compute this bandwidth. I mean, and we're not there yet, but in this talk, what we're doing is we're giving a first approximation. So we're taking bandwidth like this, and we're asking ourselves, well, what happens when epsilon tends towards 0? So the epsilon tending towards 0, that means the precision grows to infinity. So we're taking the asymptotic when epsilon tends towards 0, and we're asking ourselves, well, roughly, how will the bandwidth behave? Okay, so that's this talk. And of course, we will ask ourselves this question first and foremost for regular time languages. And so to do that, I have to introduce to you timed automata. So I'm guessing everybody knows how a finite automaton works. Well, a timed automaton is very similar. We have our set of states as well. We have our set of transitions, but we have some additional stuff. So we have some clocks. In here, clocks are X and Y. And the long transition, we can do 2 things with clocks. So we can test them with by comparing it to integer values. So in here, for instance, for taking this transition from P to Q, we need the clock X to be smaller than 1. And we can also reset them along transitions. So in here, in this transition, we are also resetting X. So that means when we get to Q in here, X will be equal to 0. And if we want to take this transition again, we have to arrive here we have to take it in less than 1 second. Otherwise, this card won't be satisfied anymore, and we won't be able to. So what does a run on the automaton look like? Well, something like this. So we start in an initial state with some clock vector, and we're here. And whenever we're in a state, we can wait for a little while. So in here, we'll wait for 0.3 seconds. At some point, we can decide to trigger a transition, which we will trigger immediately. So we take the transition, we reset the corresponding clocks. So we get to X equals 0 here, and then we're in Q. In Q, we can wait for a little while, and at some point, we will fire the transition if we want to, and if the guards are satisfied. So an important remark here is that contrary to finite automata, when what's important in a sense is to know which state you're located on. For timed automata, you need to know not only which state you're on, which location you're on, but also what is the clock vector where you are. Because if here we had an x greater than 1, the reachability is very different because we cannot take this transition. So the problem is, of course, that for analyzing this, there's again an infinite amount of clock vectors. So for analyzing this, we need to stuff them together in a sense. So we're defining what's called clock regions, so that different clock vectors will belong to the same clock region, and we will have a finite number of clock regions. So what we want these clock regions to be is, so we want these clock regions to have two properties: that whenever two clock vectors are in the same clock region, they satisfy the same set of guards. So that means the integer part, the integer part of any clock has to be the same in both. So in here I have drawing for a case with two clocks, x and y. So we want that whenever two clock vectors are on the same region, x and y satisfy the same guards. So this is the vertical and horizontal lines. So that's the integer part in any of these squares. The integer part of x and y is the same. But we also want that after a time delay, the guards that are satisfied are the same. And so if we look at this square, like if we're in the upper part, after some time, we will reach this square, whereas if we're here, we will reach this one. So this part of the square and this part of the square cannot belong to the same region. So basically what that means is that the fraction in every clock vector in the region, the fractional parts of any two clocks have to be ordered in the same way, because that way the first clock to change its integer part will be the same in both cases. Okay, so this is basically what regions look like in a two clock setting. In higher dimensions, it's always regions are always simplices, sorry. And you have to also know that, so in here we have a region which is a triangle, but also every face of a region is a region as well. So we have lines in here, and we have these vertices that are regions as well. Okay, so once we've done that, we can transform our automaton, and we can put it in what we call a region split form. So a region split form is, to transform our automaton into a region split form, we're going to, well, split some locations, and we will have potentially an exponential growth on the number of locations. But the idea is that once we do this, for every location, we will have a unique clock region, which is going to be called the entry region of this location. So I have an example here. We have this automaton, as you can see, where we are here from P to Q, we take this transition, but when we reach Q, we can be in a number of different regions. So the region x equals 0, the region with x between 0 and 1, x equals 1, x between 1 and 2, etc. So if we want to put it into region split form, then we're going to split this. We're going to split the state Q, and we're going to reach these different states depending on which region we enter Q on. Okay, so this transformation is actually not exhaustive. It's missing some states, but it gives a general idea of how we do this. So I mean, in here, the region is x equals 0, so it's a point, because when we reach P, we always reset x. And in here, it's always a segment 0, 1, 1, 2, 2, 3, 3, 4. Okay, so once we've done this, we can do something very interesting, and this is something we ought to put in, is that whenever we have a region split timed automaton, so every location is linked to its entry region. We can look more closely at these regions, and we can take for any transition, we can get what we call an orbit graph. So an orbit graph is we'll look at the region, we'll look at the every vertex in the region, and we'll link the source region vertices with those of the destination, and we will link them if and only if it is possible to go from the corresponding vertex in the source to the vertex in the destination. So in here we have this region y equals 0, x goes from 0 to 1, and in here x equals 0, y goes from 0 to 1, and from 0, 0 we can get to here or to here. I mean, it's easy to verify, and from 1, 0 we can go to here. So in a sense, we have written the reachability of the vertices of the region. So what we can do is that, so we did this for transitions, but we can also do it for paths. Like we can look at the transition, the reachability we get in a path, but it's actually, to do it for a path, I mean, we can look at the reachability of vertices in a path, but we can also just take what we did with the transition. So in here, I have drawn again this graph for this transition. This transition gives this graph. And if we want to get the graph of this cycle, we actually just need to concatenate these two graphs. If we concatenate them, we get this new graph on this region. So it goes from this region and it ends up in this region as well. And well, if we concatenate these two graphs, we get this graph, and we get and then it's possible to verify that it corresponds actually to the reachability between these two vertices when we do this cycle. Okay, so I've drawn the same, just to note that we can also see this as we can do this. We can see this in a matricial way. So for every graph, we can write its adjacency matrix, and we can do a matricial product to get. I mean, the concatenation of two graphs corresponds to the same thing as a matricial product. Sorry. So it's this is the adjacency matrix of. So this is from. So we enumerate these vertices. So 0, 1, and 2, 3. So I guess this is from 0, 1 to 2, 3, or something like that. Yeah, from this vertex we get to here and to here, so it's 1, 1, and from this vertex we only get to here, so it's. I mean, okay, so that I didn't take the good order, but that's basically it. And then we do the matricial product. I mean, we'll get either a 0 or a 1, depending on if there's a path or not. Okay, so what's interesting here, so these graphs in a way, so they give the reachability for vertices, but what's very interesting here is that it actually gives the reachability for every single clock vector. So any clock vector can in a region can be seen as a convex combination of the vertices of the region they're in. So for instance, if we take this point, it's going to be 0.5 this plus 0.5 this. So it's a convex combination of both. And then its reachability will be a convex combination of the reachability of the vertices, in a sense. So here, this is a combination of this and this. This goes to anywhere in here, because, I mean, this point can go here and here, so it actually can go anywhere in between as well. And this point only goes here. So if we take this, we take the convex combination, we get something like this. In a more formal way, it can be also seen as again, as in a matricial way. So we can write the vector of this point, I mean, where the coefficients correspond to the convex weights for every vertex. And we multiply this by a stochastic matrix, and the stochastic matrix has to be smaller than the adjacency matrix I talked about. Okay, so I present this because it gives a very strong result on reachability. It gives Yeah, I mean, it gives a very useful way for analyzing timed automata. So the idea of presenting this is that we asked ourselves at some point, well, so can we use these results to try to analyze what the bandwidth will be in an automaton? Like, if we look at this graph, can we get some idea of what we will have? And well, the answer to that question is that sadly we cannot. And so I have an example here of why we cannot. So I recall bandwidth is quantity of information in a sense. So I have three automata here, and if you look at this automata, they just have one location, if each of them, and in each location, when we get here, x is reset, so x goes on to 0. So the region of any of this location is just a singleton, x equal to 0, and we can always go back to x equals 0 in some way. So so the orbit graph will be something like this, with this point representing x equals 0. So they all have the same region graph. However, their bandwidth are completely different. So here, this automaton, we take this transition whenever so every second, every exactly 1 second, we have to take this transition. So we don't get a lot of choice. And so the intuition is that the quantity of information is, in a sense, how much choice do we have in the automaton, and we want to have choice with some frequencies infinitely often, in a sense. So in here, we don't have a lot of choice. I mean, we take this transition every second. I mean, the only choice we have is, well, at some point we can choose to stop the run and to say, well, we have already our word. But so that doesn't give enough bandwidth. That gives a null bandwidth. So yeah, this gives a bandwidth of 0. Then we have this automaton is a little bit more interesting. So we have, so in here we have to wait 1 second. We're at x equals 0. We'll have to wait 1 second, and then we have some choice. We can choose a delay of between 0 and 1 second, and we do this. So if we're more precise, then that gives us more choice. But we get this choosing, and we get this choosing infinitely often with some constant frequency, like every second. I mean, not really constant, but with between every 1 or 2 seconds, we get this new choice. Okay, so that gives a bandwidth that is logarithmic with regards to the precision, and then the biggest bandwidth goes to this automaton, and in this automaton we get again a choice of a delay between 0 and 1 second. But the thing here is that whenever we do this transition, then we don't have to wait for a whole second. We can trigger the transition again if we want to, or not. So we get this choice very quickly, and so in a second we have a lot of choice. We did the choice of firing the transition or not, like 1 over epsilon times, in a sense. So we get this bandwidth of that is proportional to the precision, in a sense. Okay, so that's I have gone into detail with these 3 automaton, because actually our main result is that regular time languages, and therefore timed automata have their languages can be classified into 3 distinct classes. So either a very small bandwidth, a bandwidth that is proportional to a logarithmic of the precision, or that's just proportional to the precision. Okay. Okay, so the idea is that we will have so we will take some graphs which are similar to the reachability graphs as before, but we will enrich them with some additional information. So basically the information of freedom, which is how much choice do we have, and the information of duration, so how quick we are. So we will get new graphs, and in these graphs we will define 2 patterns, one pattern implying the other. And the idea is that we'll have a sort of trichotomy. If no pattern is present, we will have a very small bandwidth. If the first pattern is present, we will have a at least a logarithmic bandwidth. And if we have if we don't have this second pattern, it's a logarithmic bandwidth. And if we have both patterns, we have a proportional bandwidth. So the idea of the proofs is that we will prove lower bounds. So whenever a pattern is present, we will deduce a large enough epsilon separated set on the language, which will give us which will tell us that the bandwidth is at least large enough. And the thing is, for upper bounds, this will be much more contrived because we have to prove that whenever a pattern is not present, we will have to cover with a small enough epsilon net. And for that, we will have to use a bound, which is given by Simon's theorem. So I won't present Simon's theorem here because I don't have enough time for that. But well, basically, it helps us have a bound of for these epsilon nets. But what we have to know is that Simon's theorem requires us to have a finite monoid structure. So we are transforming paths as before into graphs, and we want these graphs to have a finite monoid structure. So before the graphs, as we could concatenate them, and there was a finite number of them because it's just zeros and ones in a matrix. It was a finite structure. So now we have to keep that structure. So for that, we're defining new labels that we will put on our graphs. So we will say that the edge between U and V will be labeled narrow whenever between U and V along a specific path. There is only one way of going from U to V, and wide whenever there's more than one way. Okay, so this is for technical purposes. We need these labels to have a semi-ring structure because that's what will ensure that we have a finite monoid structure in when we do our matrices. Okay, so how does this look like? Okay, so I took the same automaton as before. So here we have the orbit graphs as well, but in here I have I have colored them, and reds are those that are wide. So this arrow is green. That means along this transition, there's only one way for going from here to here. The same with every green transition. And here in this cycle, there's actually two ways of going from this point to itself. So I can write it in it can be written in a matricial way as well with the semi-ring operations I presented earlier. And so, okay, so basically this is the idea of how we get these labels. And then what we get is that our first pattern that divides a very small bandwidth with the rest is to have a wide self-loop as here. So whenever we have a wide self-loop, we know that we are at least logarithmic. And whenever we don't, we know that we're very small. So the idea is that a self-loop is, in a sense, some stable behavior because we got from a point to itself. So that means we can repeat that as much as we want. And it being wide, that means we have some choice in this path. So that's basically the main idea. So well, here is an example of an automaton without a wide self-loop. So in here, every stable behavior is narrow, so that doesn't give us enough choice. Okay, so we do the same for duration, for speed. So now we're labeling with different letters, with different labels. So we get slow, instant, and fast. Slow is whenever from a vertex to the other, we have to take at least 1 second. Instant is whenever we have to do it in 0 seconds, and fast is when we can do it with any duration between 0 and 1 second, basically. So we get as well a semi-ring structure. We get as well a pattern. So the pattern is this or that. And whenever we have this pattern, we're at least proportional. And whenever we don't, we're at most logarithmic, basically. So yeah, so it's very similar. I mean, this is a little more contrived, but this part of the pattern is very similar, just having a fast self-loop That means we can have a stable behavior that is very quick. Okay, so basically with this, we can decide what the class of a timed automaton is. And so this is p-space complete. So p-space membership, we just have to look for the pattern, the bound, and there's a bound given by Simon's theorem, and p-space hardness is reduction from reachability. And so yeah, that concludes. So we've introduced a notion of bandwidth. We have classified automata according to their bandwidth when the precision grows to infinity, and we have given structural criteria for that. And well, future work. I mean, I took this slide from my supervisor, so I may not have the insight of everything that is written here, but currently we're working on this part. So we're trying, so we got like the class of the timed automata, and now we want to compute it more precisely, and we're currently working on computing it for the smallest class of timed automata. And that's all from me. Thank you. Yeah.
What we directly this work, but maybe more pertaining to previous work which you referred to. So what is the
studying this information theoretic aspects of languages and more in particular to timed languages? Like
Yeah.
in what contexts these things are used?
Okay, so yeah, so like the information theory aspect, well, it has been studied a lot for regular languages, so that's already that framework that we want to kind of emulate in the time setting. And so yeah, and so like the question is I guess, what does time behavior bring to the table?
Yeah, or in what contexts this might be useful and
Okay, so yeah, I'm not that knowledgeable about applications, but I've heard, for instance, like to give an example of what I've heard my supervisor talked about. So he talked about in a cryptographic setting. So you may have like some leaking of information that some attacks that could exploit like the time at which you're producing your message. So like in a sense, you would like that information to not leak. And so in that way, maybe you would need to know which information is leaving, of which time the information is leaving. So that's basically the example I can think of.
okay, yeah, thank you.
Thank you for your talk. So I wanted to ask if by any chance work on this kind of thing has been done for timed models which are not just the regular timed automata.
Not that I know of, at least. Yeah, so yeah, not that I know of. So yeah, like I mean, I've been working working with my supervisors for like 2 years now. I know they did like some very similar previous work in which they did some information theoretic stuff, but they had a notion of information not per time unit but per event, but it was still on timed automata. So
Okay.
yeah, that's all that I know of.
Okay. Thank you.
Any further questions? Since there is no other talk, we'll take a couple of more questions.
Is there a specific reason why you chose that distance metric?
Yeah. So okay. Yeah. So I went a little quickly because of time, but so yeah. So this distance was actually introduced by my supervisors with kind of this in mind. So as you can see, there's some details about this distance that So the words can be close to each other, even though their letters are not in the same order, and I mean the number of letters may not correspond exactly. So basically, as we're looking at as we're concerned with information per time unit, so basically this allows us to. So the thing is, we want our epsilon nets to be finite whenever time is bounded, basically. So that's compactness, and for that we have to lose the information of the order and of the quantity, because otherwise in a language of 1 second you could get like in automaton that just can output a letter at each possible time in 1 second. So you get like a language of 1A, then of 2A's, then of 3A's, and like every single possible number. So that's like already infinite. So you have to lose that information. You cannot count how many letters there are. And I mean, and for order is kind of the same, because I mean, you just need to consider 2 letters, and if you consider their order, you basically can go back to how many letters there are.
Thanks.
Yeah, this is probably not a smart question, but so when you were showing the characterization for obese, the pattern, the second pattern, which had like instant things and a slow.
Yeah.
So is that at least slow, or is that like if the central edge was fast, does that also work, or is it exactly slow?
Okay,
Yeah,
so
Is that at least slow, or does it have to be exactly
okay,
slow?
so actually yeah, so the thing is that okay, so keep in mind that these arrows are written for a specific path. So you have to fix the path, and then you get the graph. Okay, so the thing is, so we have 2 vertices in a region, and along a path, if you do the path so the thing is, like, you cannot do. So the path is fixed, and what changes when the path is fixed is the delays. I mean, the times at which you take the transitions. But so as we have an instant arrow here, that means that if we take that path with 0 seconds, then we'll get to itself. So you cannot have a fast arrow here, because a fast arrow here would mean that you can do the path in either 0 or 1 seconds. And in 0 seconds, you get to here. So you cannot get to here, because I don't know if I'm clear, but yeah, so you cannot have a fast arrow here. And yeah, so to give a quick remark, so this is basically like, personally, I see it like as a degenerate version of fast. So the idea here is that we have a stable behavior that we repeat very quickly. And in here, the idea is that the combination of these instant and slow arrows means that we can go like very quickly in here, but as we do it, we're like kind of going forward in this arrow, because I mean, if we want to stay here, we have to do it with 0 seconds, and 0 seconds is not distinguishable. To distinguish it, we have to go at least epsilon. And so we're going forward in here, and at some point we will run out of time in a sense, so we need another pad to take us back to kind of charge the batteries. Is there another question, or that's okay? Yeah.
Let's thank. So that's the end of the session. As I said before, the other talk is not happening.
Have to turn this off, or you can turn this off. That's good.
Um,
Hello, hello. Yeah. Yeah. Okay. Hello. ठीक है ठीक
Start with Patricia, should we?
Yes.
Yeah, I think it's time. Okay. I think we can start this session. So welcome back after the break. So in this session, we will have two talks, one by Abhimanyu and one by Abhishek. And both will be in the themes, will be related to proof theory and different aspects of it. So our first talk is by Abhimanyu, and he will be speaking to us about dependency schemes in CDCL-based QBF solving, a proof theoretic study which ties well with the SAT assembly workshop too. Okay, over to you.
Hello, yeah, thank you. So today I'll be talking about dependency schemes in CDCL-based QBF solving. It's a work I've done with my supervisor, Meena Mahajan. And so without further ado, I'll start. So the outline of the talk, I'll basically talk about first what I mean by QBFs or quantified Boolean formulas. I'll introduce them, give a bit of idea about the semantics. Then I'll go into what QCDCL or what quantified conflict-driven clause learning means and give a basic overview of how we can understand it. The third thing I'll cover is the other term in my title, which is dependency schemes. We look at what dependency schemes are, why they're interesting, and why we want to study them. And then finally, I'll motivate why we want to add dependency schemes to QCTCL, why we want to mix them up, and how it can actually help us, and what results we have achieved in doing the same. So, yeah. So first, let's start with QBFs. So what are QBFs or quantified Boolean formulas? So basically, we all know what propositional formulas are. In propositional formulas, we have a notion of satisfiability, which is very common to us. So QBFs or quantified Boolean formulas are basically just an extension of satisfiability. To a propositional formula, we just associate a quantifier prefix and we call it a quantified Boolean formula. SAT effectively is a special case where each variable is quantified existentially, but now we also have the option of an extra quantifier, the universal quantifier, and each variable is assigned some quantifier which we put in front of the formula. And now the question changes from satisfiability to whether my formula is true or false. So let's look at an example to understand what I mean by that. So suppose we have a simple formula, there exists x for all y, x or y, and not x or not y. So is this formula true or false? So we say this is a false formula. Why? Because we look at x. If x is equal to 0, then y equal to 0 falsifies the first clause. So the entire formula evaluates to 0. And if x equal to 1, then y equal to 1 falsifies the second clause. So the formula again evaluates to 0. So there does not exist an x for such that for all y the formula is true. So therefore it's a false formula. Now we look at another example. If we say for all y there exists x or y, and x bar or y bar. Here we've just switched the order of the quantifier. Now this formula becomes true. Why? Because for y equal to 0, if we choose x equal to 1, then the formula evaluates to 1. And for y equal to 1 and x equal to 0, the formula again evaluates to 1. So for all y's, there is some x such that the formula is true. So this is a true formula. Yeah. So basically, fact to notice for SAT, it does not matter how the quantifiers look, but in a QBF, for the same formula, if you just switch the order of the quantifiers, whether the formula is true or false, it can change. This is important. So the order in which the variables are placed in the quantifier prefix is important to whether a formula is true or false. It's just not what the formula is. So let's look at how we can understand QBFs a bit differently. We can look at QBF as a two-player game. How does this game work? There are basically we say there are two players, an existential player and a universal player. The job of the existential player in the game is to assign values to the existential variables, and the universal player assigns values to the universal variables. And the game proceeds in the manner as according to the quantifier prefix. We look at the first variable. If it's existential, the existential player gives it a value. And if it's universal, the universal player gives it a value. And the game ends when all the variables in the formula have been assigned a value. So let's look at a sample run of the game. So initially here, we start off with the first variable, which is x. Suppose the existential player assigns x equal to 0. The universal player assigns u equal to 0, and the existential player then assigns t equal to 0. What happens is, we say that the universal player wins this run of the game. Because for this set of assignments, the first clause, if you look at it, it evaluates to 0. So the entire formula, we say, has evaluated to 0. So the universal player wins the game. Another run of the game could be slightly different, where the existential player plays x equal to 0, universal player plays u equal to 1, and existential player plays t equal to 0. In such a run, we say that the existential player wins because all the clauses have been set to true. So the entire propositional formula in this run of the game has been set to 1. So the existential player wins this game. Quickly, let's look at a third run, where we say that the existential player plays x equal to 1, universal player plays u equal to 1, and the existential player plays t equal to 1. This time the universal player wins because the last clause is falsified. It evaluates to 0. So in this example, we can say that if proceeding in order, if the universal player plays u equal to x, since the universal player will always decide u after the existential player has decided x, if he decides u equal to x, this formula can always, or universal player can always win this game. How we say this is looking at the goal in the two-player game, because we say that the goal in the two-player game is for the existential player to satisfy the formula, basically evaluate the propositional part to true, while the universal player is looking to falsify the formula, basically evaluate the formula to false. And we say that a QBF is true if and only if wait just a sec. So a QBF is true if and only if the existential player has a winning strategy in the two-player game, and the QBF is false if and only if the universal player has a winning strategy in the two-player game. So this is how we define the two-player game on a QBF. And a quick notion on QBF proof systems. What is basically a QBF proof system is basically a set of rules used to prove whether whether a formula is true or false. We'll focus on refutational proof systems. I'll talk basically focusing on trying to prove that the formula is false. And the notion on how we'll go about it in the proof systems is basically, we say that a formula will be false if the existential player can never win the two-player game, or the universal player can win it. And the idea will focus on basically deriving an empty clause as it has no satisfying assignments. What this means is basically, given a formula, I want to try to prove it to be false. To try to prove it to be false, what I'll do is I'll keep using the rules, I'll keep adding clauses to it by saying that if the formula was true initially, adding this clause keeps the formula to be true, and I keep on adding clauses to the formula. At the end, if I can add the empty clause, I can say that the empty clause, which has no literals, can never be set to true. So since this empty clause can never be set to true, the existential player cannot win on this formula with so many new clauses. So the existential player could not have won on the initial formula. So this initial formula must be false. So this is the idea of how a QBF refutational proof system goes. And there is the notion of strengths of proof systems. So we say a proof system A is stronger than a proof system B if there is no formula which is easy in B but hard in A. By easy in B, easy I mean it has a polynomial size proof, And by hard, I mean it requires an exponential size proof. So, and apart from no formula exists that easy in B and hard in A, and there is at least one formula which is easy in A but hard in B. Then I say A is stronger than B. And I say two proof systems A and B are incomparable if there is a formula which has easy as in polynomial size proofs in B but requires exponential size in A, and another different formula which has polynomial size proofs in A but requires exponential size proofs in B. Then I say A and B are incomparable proof systems. So next I'll go into what QCDCL or quantified conflict driven clause learning is. So this comes from quantified comes from because this is for QBFs. Conflict driven clause learning, as if you attended the SMT workshop would have seen, is basically I'm trying to construct an assignment to satisfy my formula given to me. If I cannot, I reach a conflict, means somehow my assignment is falsifying my formula, and from this conflict I learn some new constraint. So this is called clause learning. So I learn a new clause which I add to my formula and say that because in my efforts to try to prove the formula to be true, I've reached a conflict, and from this conflict I can learn new things which can tell me how I can go about in my next steps on trying to prove the formula again. So basically this started off being an algorithm which it was written to decide whether the formula is true or false. Based on this algorithm, a proof system was also defined, which was called the QCDCL proof system, which basically underlies this algorithm and gives the theoretical proof system on which the algorithm is based on. And this also focuses on false QBFs, which is basically trying to refute or prove a formula to be false, and therefore it considers the algorithm from the perspective of the existential player. By what that I mean is, I start off from the perspective of the existential player, and I'm trying to prove the formula to be true. I'm trying to, and ultimately I end up showing that the formula cannot be true, and therefore I conclude that the formula is false. So basically, this goes about in two steps. Basically, I try to construct an assignment of all my variables, which I call a trail, which tries to satisfy the formula. And when I fail to do so, I get an assignment which falsifies my formula. I call it a conflict, and from that I have a set of possible clauses or new constraints that I learn, and I learn one of them according to some policy. So how do I construct my trail? So the rules in constructing a trail are straightforward. First, I look at my formula. If any existential must be set to ensure the satisfaction, we call it a propagation. We force it to be true. By what that I mean is, since we are looking at the perspective from the existential player, we are trying to satisfy everything. So if we see that there is a variable which must be set to such that for a clause to be true, we set it in that way and we call it a forced propagation. If we cannot, there is nothing to be forced, then we must decide some variable randomly, and we decide variables on, there is a restriction on the order. We look at, since QBFs, the order of the variables is important, we look at the first variable which I have not assigned a value to, and I assign a value to it, and then I move on. Then I try to do propagations, that I keep doing it until I hit what is a conflict, which I say that the trail forces one same existential to be propagated or set in two different polarities, or I say that I falsified a clause in my formula. And from this conflict, I can and how do I go about learning? There are two rules. One is basic resolution and reduction. Resolution is basically I have two clauses with one existential and opposing polarities. I can remove it and join the two clauses. And reduction is basically if I have a universal trailing right at the end, I can drop it because I'm looking at it from the perspective of the existential player. So if A or U has to be satisfied, since U is going to be decided anyway after everything in A, the existential player has to make A true for A or U to be true, because we assume that the universal player is always going to be try to falsify. It's always going to be oppose what the existential player is trying to do. So these are the two rules which we use in learning. So a quick example will perhaps make it easier. So suppose I've been given this formula, and I want to say how do I go about it. Initially, if I look at the formula, there is nothing forced. There is nothing forced. So I must decide. So first I must choose to decide x1. So suppose the moment I decide x1 to be true, what happens is the x1 bars, those two clauses, they shrink away. Then next, suppose I decide x2, then again this x2 bar, this clause shrinks. So at the first and the third clause have been set to true. Then again nothing is forced. I decide U1. Once I decide U1, this the second clause shrinks, the first and the third are satisfied. But now T1 is forced because X1 and U bar have been set in a different manner. I am forced to set T1 because of this clause. So the existential for the existential player to have any hope of satisfying the entire formula, T1 must be set to true. So existential T1 is forced, it's propagated because of this clause. Once T1 is propagated from the last clause, T2 bar must be propagated. Otherwise, because that is the only way the last clause can also be satisfied. So I propagate T2 bar, and now I've reached a conflict because this clause X2 bar, U2 bar, T2 cannot be satisfied by the existential player anymore. So I've reached a conflict. So this is how a trail goes. Now I have reached a conflict. From this, during the resolution and reduction, these three lightly shaded clauses are my possible set of learnable clauses. I can choose to learn any one of them. Suppose I learn the first clause. How does this go about this? Is now I have added this clause that I learned from the previous. It gets added to my formula. So once it gets added to my formula, how does it change? Next time I'm trying to create a trail. Suppose I set X1 again. This time, earlier in the first time I couldn't force anything, but now I'm forced to set X2 differently. So I'm forced to set X2 bar to proceed, but then again nothing else is forced, so I have to decide U1, and then I can then I proceed in the same manner, T1 T2 bar, and again this time I get a conflict because of that clause can no longer be satisfied, and then again I have a learning process such that this time I can choose go back and so I can learn X1 bar. So this is how in general the QCTCL algorithm proceeds. I have a trail, and from each trail I learn something. So in general, a proof in the QCTCL system would look like TC pi, where T is the set of trails. From each trail, I have a corresponding clause that I learned, and pi is basically a derivation of that clause in using those two rules. And I say the algorithm ends when the empty clause is learned, because when I learn the empty clause, I can say that I've proved the formula to be false. So this ends. So an algorithm ends when the empty clause is learned. So next is dependency schemes. So what are dependency schemes? And why do we study them? So dependency schemes basically comes directly from the notion of in QBFs that the quantifier order is important. So trivially, every variable appearing to the right, so every variable depends on everything appearing in the prefix before it. So what that means is basically I must respect the quantifier order. So if I have U or X, for all U there exists X, for all Y. So X depends on U because X appears after U in the quantifier prefix. This is trivial dependencies, and what we want to do is find a way to identify and discard spurious dependencies, because just because a variable appears after 10 variables does not necessarily mean its value depends on all of them. And how do we define this notion of dependency is basically we say again in existential X is independent of a universal U. If the existential player could have won the game, then the existential player can still win the game by choosing a value for X without knowing U. Trivially, if X appears after U, we say that to decide X, I must know U. But suppose I could win even without knowing U, setting X without knowing U, then I say X is independent of U. So this, if you look at this formula, the two formulas, in both cases, we can see that the existential player can win. But on the formula on the left, we say for the existential player to win, X must be set opposite to U. Then only the formula is true. So in that case, X depends on U. But in the right formula, without knowing U, X equal to 1 is a way of satisfying this entire formula. So here in this formula, X is independent of U. So this is the notion of independence. So why do we study them? Because in general, we said in the reduction rule, if U appears before X, we cannot say throw away U. But if we know that U is independent of X, then in a clause with U or X, we can just throw away U and get a shorter clause. So how that helps is because suppose we have discarded more dependencies, then potentially these more reductions could be done. And once potentially more reductions could be done, in a clauses, I can throw more things away. So theoretically, I should be able to get the empty clause, which is my goal, faster. And in fact, there exist dependency schemes when added to proof systems, provably strengthen proof systems. So this is the notion, and one such dependency scheme is the one we studied in detail, which is the DRRS dependency scheme or the reflexive resolution path dependency scheme. Again, this is the same formula, and trivially we know that all the T's depend on U. So U1 T1, U1 T2, U2 T1, U2 T2 are the dependencies. And how we look at how the dependency scheme further modifies and reduces these dependencies. So the notion of resolution, there is a notion of resolution path. The notion of resolution path is such that from U to T, there is a resolution path if there is a sequence of pairwise complementary literals which can lead me from a clause with U to a clause with T. So in this case, from U1 to T2 bar, I have a clause with U1 T1 and I have a clause with T1 bar T2. So this is a resolution path from U1 to T2 bar. This is an invalid resolution path, even though U1 and X1 appear together and X1 bar and T1 appear, but X is to the left of U, so it's not allowed. So we cannot. So this again is an invalid resolution path because though U1 T1 appear, T1 bar T2 bar appear together, but this is not pairwise disjoint. So we do not have an even length. So there is one literal missing. So this is also an invalid path. And finally, if you look at another path, here this path we say is invalid because the path uses U2 and U2 bar. We are not allowed to use universal variables. So effectively, in this DRRS of this formula effectively becomes the empty set. There are no dependencies, where the DRRS dependency says if there exists path between ux and u bar x bar or ux bar and u bar x via existential variables to the right of u. And here for this formula, it's not true. I won't show all of them, it will take too much time, but it's not. So there are no dependencies in this formula. So let's go into our work. So our work is basically adding this dependency scheme DRRS to QCD-CL. And the motivation is that since in theoretical proof system, we see that it adds strength. So does it do so for the QCD-CL system as well? And how does it affect the strength of the system? So we say there are two ways of adding. One is in pre-processing and one is during the propagation and the learning. I'll go into details of how they are done. And the third is we say that we do it in both cases. So there are three new systems that we study. The first is basically when we do it for pre-processing. For pre-processing, it's straightforward. Given a QBF file, we calculate the dependencies and perform all reductions. So in basic, there might be more reductions which are enabled by the dependency scheme, which we couldn't do earlier. We do those reductions and get potentially a sub-formula of my initial formula. And then I just do QCD-CL on this new formula. This is basically what I just call pre-processing. So if you look at this same example, DRRS was empty. So what we can do is we can just remove all the U's, get this smaller formula, and do QCD-CL on this formula. This is just the simple notion of pre-processing. And when I say go into in processing or during propagation and learning, what I say, same formula, I have this notion. Normally we saw that we had this trail. We needed X to decide so many before we could force something. Here it becomes different because the moment we set X to true, what happens? We can throw away all the U's. And the moment we throw away all the U's, we see that for the second clause, where earlier even U1 had to be decided, immediately we can say that T1 must be set to true. So immediately we propagate T1, which propagates the last clause, T2 bar must be set. And then we see that the third and the fourth clause, X2 and X2 bar, both must be set to true. So we can do it in either order. And we say that we have reached a conflict. And from this conflict, again, using backward learning of resolution and reductions, we can learn X1 bar, which earlier took us two trails. In the first trail directly, with these reductions, we can learn X1 bar. And so what we've done is, given the first trail, we have been able to add X1 bar. What this does, which we haven't been able to done so far, we start off with any trail by forcing X1 bar. Because this X1 bar has to be true, we start off every trail by forcing X1 bar. And again, forcing X1 bar forces us to propagate T1, which propagates T2 bar from the last clause. And we reach the same conflict that we reached earlier. And this time from this empty conflict, we are actually able to see that we can learn the empty clause. So basically in two trails, we've been able to learn the empty clause, which basically completes the refutation of my formula in this new system. So earlier we took us two trails to just learn X1 bar. Here in two trails, we have been able to refute the formula. So trivially, it looks like basically doing more dependencies will doing more dependencies just seems to add strength. We could do things in lesser number of trails right now. So, but that is actually not true. We see that we have these three notions where we add it in pre-processing, in processing, and we do both. Trivially, it seems doing it in both should be better, but our results show that these systems are all incompatible. In fact, we have seen that doing it in both could actually be worse off than doing it in either one individually. So there are formulas which could, when doing it in both, we require exponential size proofs, but have short polynomial size proofs when we just do it in one side. And it's not just that. If you just look at basic QCD cell, comparing it with basic QCD cell, all of them are individually incomparable. So there are things that we can just do in basic, easily done in basic QCD cell by adding more power, allowing more reductions, and even starting off with a smaller subformula of the formula could in fact make things harder. So it basically seems counterintuitive that basically starting off with a smaller formula than the initial formula, things become harder to prove. And then there's another proof system which is basically stronger than the QCD cell, which is QCD cell cube. The notion of QCD cell cube is more realistic because so far QCD cell just focuses on learning from things when I reach a false conflict. But it's not necessary that I'll always reach a conflict. Sometimes while constructing, I might reach a true assignment. That does not make my QBF true. But in those cases, instead of wasting such an assignment, I can learn things from a true assignment as well. And that is provably a stronger proof system than the QCD cell. And adding dependencies to this QCD cell is in fact incomparable even with the stronger system, as well as a host of other systems that we show where QCD cell level ordered is a special restriction of QCD cell. QRes is the standard system which has resolution and reduction. QDRRS, which was one of the motivations of trying to do this work, is where we add the dependency scheme to QRes. It gives us a strictly stronger system, but this strictly stronger system is still incomparable with all the systems that we have looked at. So I'll skip over this. I think I'm out of time. So future directions. So in this talk, basically we looked at adding dependency schemes to QCD cell. We hoped of getting a stronger system, but we haven't. So futurely, what we can look at basically adding other dependency schemes, D standard, which is a bigger class, more weaker notion, or implication-free dependency schemes, which are even stronger, and hopefully adding them, if they could somehow give us a concrete information on adding strength to a QCD cell instead of just becoming incomparable, giving a stronger dependency, or adding dependencies to the QCD cell cube system, where I learn things even from satisfying assignments, could potentially two future directions that we are currently looking at. Thank you.
Questions? Yes, Anupam.
Thanks. I have some naive questions actually. So I think it was maybe implicit in what you were saying that when you look at the trails, they kind of give a uniform description of plays of strategy.
Yeah.
Right. So is that clear that from a QCDCL proof you can extract a polynomial size strategy in the QBF game?
From QCDCL.
I guess by taking the universal variables and just branching into zero.
So from the entire proof, you can effectively, because from the given entire proof, you can extract a strategy for the universal player to win the game.
Right, and because you're kind of like uniform in the universal variables, right?
Yeah, not exactly uniform, because basically you don't. Basically, you get a strategy because given basically from the trail, given all the traits, you basically have a complete proof of falseness. Since you have a complete resolution-based proof, from that you can easily extract a strategy for the every universal variable in polynomial time.
Okay, and then when you added the dependency schemes, is it still the case? Do you get strategies that satisfy the dependency constraints?
Yeah.
Okay.
So they'll satisfy the dependency, because the proof we extract from basically from the QCD cell, you can extract a resolution-based proof, and that resolution-based proof also respects the dependency. So you'll get strategies which respect the dependency scheme.
Okay, thank you.
Yeah, sorry. At the beginning of the talk, you compared systems with respect of polynomial and exponential size
Yeah.
formula creation. Is there any proof that always either one of these happens for cases? So couldn't it not be that one system produces only some, say, quasi polynomial size proof or something like this? Is this disproved?
I think it's possible, but I haven't actually come across that separations in that, like a system producing only quasi polynomial size. So it's possible, but
So you say if there is an unlikely assumption true, like P equal P space, one could build something like this. Yeah.
At most one quick question. Okay, maybe I can ask. Oh, so quick. So all of these incompatibility things you have witnesses that it's not an existential proof. It's like you actually give witnesses that
yeah,
show that
there are formulas which witness, so like
which are easy in one and
easy
hard
in one, yeah, explicit formulas for each incompatibility, which is easy in one and hard in the other.
I see. And the hardness proofs, how do you typically show them?
The hardness proofs basically come from resolution based hardness. Basically, the hardness proofs in our paper, basically those formulas those formulas become basically hard for SAT, and they become reduced to basically propositional hardness.
Propositional.
So it comes from propositional hardness.
Okay. Okay, I think in the interest of time, we should go to the next talk. So thank you. Everyone, let's thank the speaker. Yeah. Next speaker is Abhishek De from.
Maybe you had occasion.
Yeah.
I think for me, it's that's okay. Maybe oh,
Okay. So. Right. Okay. So let's begin. So we have our next speaker, Abhishek De, and he'll be speaking to us about comparing infinitary systems for linear logic with fixed points. Yeah. Over to you.
Thanks, Abhishek, for the talk. This is a joint work with Anupam Das, who is also here, and Alexis Sona in IRIF. So this is a talk based on a fixed point logic. So I'll just get right into it. What's a fixed point logic? It's a logic where you can talk about fixed points of functions. So it's like an operator, which you add to the logical language. In this talk, we'll have mus and nus, which refer to least and greatest fixed points, and they will be duals of each other. So we'll have this object, which will refer to the fixed point of the function, which is phi here, and phi is a function over x. And ideally, an ideal semantics would say something like this should hold, that if you apply phi to it, you get the same thing. So the question is, why do we do fixed point logics? And it really depends on the community, who you ask, and what sort of logics you work with. If you extend propositional model logics with fixed points, you will have things like LTLs, you will have model mu calculus, and this is something which is very common in model checking, and you would want to express a lot of rich specifications, like something happens infinitely often and so on. If you extend first order logic with fixed points, like least fixed points, inflationary fixed points, and so on, it's a huge world of descriptive complexity, and all the zoology of complexity classes can be characterized by these sort of logics. Then you have algebraic logics like linear algebras and action algebras, and it is helpful to axiomatize formal language theory. And the Kleene star there is basically a least fixed point. And then finally, we come to my setting, which is the extension of linear logic with fixed points. And this is something which has been quite useful in automated reasoning, where you want to prove things by induction or co-induction principle, and also in PL semantics. Anupam gave a talk, or will give a talk in RHPL about PL semantics of fixed point logics. So this is my plan. I'll talk about linear logic so that you know what I'm talking about. Then I'll concentrate on mu-mal, which is the extension of fixed point logics with, extensions of linear logic with fixed points. And I will give you 2 proof systems. And this talk is about comparing those 2 proof systems. So I'll prove an inclusion result, and I'll prove strictness of inclusion results. And along the way, I'll prove an upper bound on something. So the idea is that the fun part about this paper was we used a variety of techniques, and I would be happy if you appreciate those techniques. And these are like broad spectrum antibiotics, right? So these techniques are not really bespoke to the situation we are in, and maybe you will have some cool usage of these techniques. I do not claim ownership of these techniques. It's just it was fun. So yeah, so this is linear logic. So if you give a sequence system, you have some structural rules which sometimes you do not really write explicitly or do not care about, in the sense that, in what sequence am I using some formulas? So basically, I can exchange 2 formulas, or I can use 2 formulas twice, or I can forget about a formula if I'm not using it. Basically, this is talking about the data type of the sequence. So if you can exchange formulas, you can think of them as multisets rather than lists. If you can use them twice, you can think of them as sets rather than multisets, and so on. But in substructural logics, you are not allowed this freedom. And these structural rules are sometimes absent, sometimes restricted. In linear logic, we do not have the contraction and the weakening. We still have the exchange. So this is what a typical linear logic system would look like. Because of the absence of contraction and weakening, we'll have 2 sorts of contraction and 2 sorts of conjunction and 2 sorts of disjunction. So we have the multiplicative conjunction, for example, which splits the context, and it really remembers the context. So in a way, it's like resource conscious is what we call in the linear logic community. Whereas in here, it is kind of copying the resource, which is the width is the additive conjunction. Consequently, because of having these 2 forms of conjunctions and disjunctions, we also have 2 forms of truth and false. An important rule here is the cut rule, which is always there when you're working with sequence systems. And as I told you, you have the exchange still. So I won't really refer to it. So mu-mal is adding fixed points to mal, multiplicative additive linear logic.